Okay, now you should see my screen. Okay, I see some people nodding. Thanks. Thank you very much for the nice introduction. And we were discussing just beforehand that so Mark just introduced basically the part that I was planning to skip. Before I delve into my current research, I would like to give you, some idea where I'm coming from. So I will not start with the high seas mission. I will start with another mission that happened beforehand, which only was 2 weeks. And the background was that when I was in Finland, I had this opportunity, or there was the Mars Society that was looking for volunteers to simulate life on Mars for an entire year in the Canadian Arctic. And if you listen to Mark's introduction, then you know I'm attracted to the cold, I'm attracted to the north, I like snow, I like ice. And that was initially my motivation to say, ooh, this sounds really interesting. I want to participate in this mission. It's going to be a year in the Arctic. That sounds like fun. There were some problems with this mission, but during the selection process, selecting the people who would participate in this mission, I had the opportunity to go to the Mars Desert Research Station in the desert of Utah for 2 weeks, together with 5 other people. And there we got already a glimpse of what it means to simulate life on Mars. So we had no contact with the outer world except for time-delayed communication. And every time we wanted to go outside, we had to wear mock spacesuits. And so, like I said, this was our first glimpse into this whole world of simulating life on Mars. And when it became clear that this project wouldn't take place, about at the same time, there was a different organization coming along, also looking for volunteers to simulate life on Mars, also for 1 year, but not in the Canadian Arctic, but on Hawaii. And my first reaction was like, Hawaii, simulating life on Mars underneath the palm trees and close to the beach, or what is this supposed to be? But then when I did some research, I saw, okay, this is on the flanks of a volcano, and you can see in the photo the environment is quite realistic. Also geologically speaking, the Mauna Loa volcano, where the high seas habitat is located, it's a shield volcano. And on Mars, there are shield volcanoes, and also the chemical composition of the rocks on Hawaii is very similar to what you would find on Mars. So quite a realistic setting from various aspects. And at that time, to my surprise, I was selected for the crew. And then I went on to simulate life on Mars for an entire year with 5 other people. And again, the conditions were we had all our communications were delayed by 20 minutes each direction. And when we wanted to go outside, we had to put on our suits. And also, it's not like we could go outside every time we wanted to, but beforehand, we had to apply to mission support and let them know that we were planning to leave the habitat. So quite different from how it's normally done in your everyday life. And this mission was funded by NASA and conducted by the University of Hawaii. And then in 2017, I was asked if I wanted to participate in another mission. And I mean, you would think, after simulating life on Mars for an entire year, come on, isn't that enough? And I would have certainly said so directly after the mission. But then in 2017, this mission, which is called Icarus, that mission had a very special condition. Namely, one of the crew members was physically handicapped. And so this was the very first analog mission where one of the crew members had a physical disability. So that person, he had lost his eyesight completely and most of his hands during an explosion about 10 years before. And so the challenge was, to cope with the disability and the reduction in function of this particular crew member. And the reasoning behind this is not so much because we wanted to do this for inclusion, but the reason was if we, when we talk about Mars exploration, typically what we have in mind are crew members who are completely healthy, fit, and in a full capacity of their bodily functions. And in reality, it's just a matter of time until the first accident will happen. And hopefully it's not as extreme as that explosion. But there will be injuries and there will be temporary or permanent disabilities and maybe handicaps. And so that's why this mission was conducted. And to me, this sounded really interesting, because this is an aspect that is often overlooked in Mars exploration. But it's extremely important, because only if we prepare for these kind of incidents and for these kinds of problems here on Earth already, then we have a better chance on Mars to successfully cope with them. And after this mission, I came here to the ZARM to work on what I'm going to present now. But before I go into that, I skipped this one photo on the right-hand side. One of the fun activities that we got to do. So we had a lot of work to do, and we did a lot of experiments and filled in, I don't know how many questionnaires. So I think on average, like 10 questionnaires per day during the high seas mission. But for me, the fun part, one of the most fun parts, was to go on EVA, so on extravehicular activity, meaning leaving the habitat to explore the surrounding and conduct outdoor experiments. And one of the things that we did quite often was to go into caves and explore caves. And also here, there's some applicability to real Mars missions, because one of the main reasons from a scientific standpoint why we want to go to Mars is to search for signs of life. And because the Martian surface is so extremely hostile, it's extremely unlikely that we will find extant life forms on the surface of Mars. Honestly, if I was a Martian microbe, I wouldn't be at the surface. I would be somewhere at the subsurface. So either in the rocks, buried deep below the surface, or, which would also be an option, inside caves. Because inside caves you would be protected from radiation, from space radiation, and also presumably the humidity would be a bit higher. So that's why caves are fun. And caves are also one of the more likely places. If we do want to find traces of life, then this is definitely one of the places where we should look for, not so much at the surface. And at the end of the mission, after the end of the mission, if you're interested, I wrote a book in German that you can buy, or you can also read my blog. Just contact me if you're interested. Okay, so now imagine I'm half physicist, half engineer, me living inside this high seas habitat for an entire year, and then going through the habitat every day, every morning, seeing parts of the habitat and wondering, this is something that would not work on Mars. This is something you wouldn't be able, you shouldn't have your habitat have this feature. This wouldn't work like that, and this wouldn't work on Mars, and this wouldn't work on Mars. So I started thinking, okay, and criticizing is easy, but how should a real Mars habitat look like? What kind of requirements does it need to fulfill? And to my surprise at the time, when I did some research, I found that all the existing analog habitats, or most of the existing analog habitats, they have been built for simulations. So there are some for performing studies. The high seas habitat is built for psychological simulations or psychological studies, and the high seas habitat is perfect for that. But this is something that often surprises people. The high seas habitat and other habitats is not built as a prototype for a real Mars habitat. And so together with an architect, we looked into, what kind of requirements would a real Mars habitat have to fulfill. And so we looked at about 24 of these habitats. We also looked at some Antarctic stations. We also looked at some underwater stations, and tried to collect the lessons learned from there. All the good features, because there are many, many good features in these habitats, but also the problems that would not work on Mars. And so we have this whole list of lessons learned from this review, but some of the most striking ones, or most interesting ones, I would assume. And the first one is, a habitat should be designed around the crew's safety. And this kind of sounds like a no-brainer. You say it like that, but in reality, some of the habitats have features that actually provoke accidents. So for example, like a classical problem is, to get from one story to the other, you have a ladder or extremely steep stairs. And then there are people, participants, crew members who are going up or down these stairs, trip and fall, and break a hand or wrist or something like that. And this is not so seldom, unfortunately. And of course, if you want to send humans to Mars, you have to make sure that they don't have accidents provoked by the habitat. There's enough opportunity to injure yourself, so we don't need to add to that with a poorly designed habitat. So that's why the first point, the habitat should be designed around the crew safety, and this should be one. We should anticipate physical hazards, so like don't have ladders or extremely steep stairs that are not secured in any way. But also we need to anticipate medical issues. And this could be simply someone having an accident during an EVA, coming back to the habitat, having a broken leg, for example. And so this is also something that several habitats have, especially when they have multiple stories. Then, let's say on the lower floor, there's the kitchen. And then on the upper floor, there's the sleeping quarters. And now imagine, if you have a broken leg, it might be a bit difficult to either get to sleep or get some food. So this is something that we need to anticipate. There will be accidents, and there will be a deterioration of physical ability. So one common problem in spaceflight as well is that the eyesight is affected. And so one thing that we need to think about is when designing the habitat that, you should be able to find your way even, if you have trouble seeing. And another lesson learned from our review was that a habitat, well, this depends on the mission scenario and on your mission architecture, but a habitat should have a laboratory and a meaningful workshop. And so we came across this because, many habitats do have a laboratory, but typically this is equipped with some, rather random equipment. And it's to some extent, some of the equipment could even be regarded more like toys than actual scientific experiments or experimental equipment. And so that's what we found. If you want to simulate a scientific mission to Mars, and again, this is about the requirements, what you want to fulfill. But if you want to simulate a scientific mission to Mars, you should be prepared for a scientific mission to Mars. And the final point that I would like to make, at least for this presentation, is adequate sound insulation. Make the crew feel comfortable. And adequate sound insulation, again, sounds like a no-brainer. And there was a NASA simulation back in the 90s where when you read the reports, the crew was quite explicitly complaining that, the noise insulation was quite poor. And, when they were trying to sleep, they would hear the other crew members, or like you could hear what the person next door was doing. And so back then they were already complaining. And the next habitats that followed afterwards that were being built, they could have learned from that. But again, many crews, so many reports, this is a recurring theme. People are complaining about the noise. On the ISS, noise is a problem. And it's not just about, there's a noisy environment, but it affects sleep. And obviously, if you cannot sleep properly over an extended period of time, it will be difficult to keep your performance up and to really fulfill all the mission goals that have been set. So this would definitely be a great contributor to sleep and performance. And in the same area, customizability and sensory stimulation. Imagine a Mars crew, they're inside this habitat for a very long time. Depending on the mission scenario, a typical scenario would be 1.5 years. So imagine being inside the same building, the same place for 1.5 years. And you can only go outside maybe 2-3 times a week, and that's quite often actually. It might be less to do an EVA. So 1.5 years inside, you're always surrounded by the same walls, by the same colors, by the same smells, by the same people, by the same stories of these people. And for your brain, this is extremely depriving of stimulation. And this actually leads to the point that psychologists are worrying about the crew members that they can remember the training that they have received before they have even left Earth. And so that they can really, use the training, the skills from the trainings and the knowledge from that training during the mission, but by the time that they need it, it will be months and years into the mission. And if the crew is deprived of sensory stimulation, if their brains are deprived of sensory stimulation, it's like, it's like a muscle. If you don't train it, it will deteriorate, it will degrade, and will be not as powerful as it used to be. So now you imagine a crew whose training was long time ago, and they're also not at their peak of their performance. And from a habitat design point of view, we should do everything we can to give the crew as much sensory stimulation as we can. So after learning all these lessons, we said, well, okay, we want to, we want to understand better how habitat systems function and how they need to work with each other, and how the crew needs to interact, or how we should design the habitat so that the crew feels comfortable inside this habitat. And so as a baseline, we came up with the MaMBA concept. So the MaMBA concept is one idea how you can build a habitat. And the goal is to have a prototype for a Mars habitat. So our goal is not to actually build the habitat and to send it to Mars. That we cannot do. I would like to, but I mean, unless Mark can attract some serious funding, we won't be able to do that. But what we can do is look at a concept and design it in a way, and make it in a way that it can be used as a blueprint for a real habitat. So consider all the things that we were criticizing before and try to find a solution to make it better. So one of the things, thinking back of the safety argument, when you remember the high seas habitat, which is this nice, wide, dome-shaped, this nice dome habitat. It's very beautiful in this landscape, but if you, inside this single module, if you ever had a fire, if we had a fire at high seas, we would have just left the building. If a crew on Mars has a fire inside their habitat, they need to be able to deal with it. And I mean, ideally, of course, we do everything that to avoid fire inside a habitat, but if there is a fire anyways, we need to make sure that the crew can combat this fire as best as possible. And one relatively easy way, if you know beforehand, and if you consider this beforehand, is to have a habitat that consists of several modules. So if you have a fire in one of the modules, you shut it down and you evacuate the crew to the remaining modules. And this is by far, this is not something new. This is done on the ISS. Not only because of the fire hazard, but it's a nice side benefit. And so we said, okay, our habitat needs to have several modules. They need to be combined, and ideally in a way so that if one module fails entirely, it needs to be shut off. If one module fails, the crew still needs to be able to get to all the other modules without having to leave the habitat. So that's why we have this collection of modules here. They're all cylindrical in shape. And those 6 modules, those 6 cylinders that you see from above, they're all connected by at least 2 passageways. And so this is the idea of the MaMBA concept, to have several modules, connect them, and each of these modules has its own functionality. This is another lesson learned, that the crew, especially on the ISS, but also during many analog missions, the crews often complain that, during the day they're working, and then in the evenings, when in theory they it's their off time, it's their leisure time, but they're still in their work environment. So they can never really shut off from this work thinking. And so that's why we said, okay, we need to separate these functions. And so the top line of modules consists of the working modules, or work modules, and the lower row here consists of the habitation modules. So we have one module for sleeping, we have one module for eating, we have one that we call the leisure module. This would be the equivalent of the living room on Earth. And then we have 3 modules for working. So one is the workshop, because, it's out of question. Things will break and things will need to be repaired. We have a greenhouse here, also where Jim is. And in the center, we have the laboratory module. Because the MaMBA concept, the idea is the MaMBA habitat is for the very first crews to arrive on Mars. I think this is important to understand. If you really want to think long-term Mars exploration, I mean, you wouldn't import your houses from Earth. You would build your houses on Mars. But for the very first cruise, to be sure that your habitat is functioning, that everything works like you want it to be, and you want to use the experience that we have from decades of space flight. So we said we want to have modules that have been built for decades already. We know cylinders work, metal cylinders, and it doesn't have to be metal, but the cylinders work, and cylinders with a diameter of about 5 meters have already been transported to space for the International Space Station. So this is definitely a size that is doable. I mean, this is quite critical. There are quite a bunch of habitat concepts out there that are so large or so complex that there's no way that they could be transported to Mars. And so that's why we said, okay, we have relatively small modules, but we have 6 of them that we can combine. And then, quite important, we will get back to this at the end of the presentation. We have airlocks. Because if you want to leave your habitat on Mars, so on the inside of your habitat, we have probably something around 1 bar, and outside we have 6 millibars. So you cannot just open your door if you want to go outside. But you need to go into an airlock, and then this airlock needs to be evacuated down to 6 millibars, and then you can leave. And same when you come back in, then the air needs to be pumped back into this airlock, and then you can enter the habitat. But we'll get back to that a bit later. And so because for us the focus is a scientific mission to Mars, that's why we said, well, if we were to build a module of these 6 modules, the one that's most interesting to us is the laboratory module. Because, I mean, creating a sleeping module, I think this is more something for architects or designers. But we're more interested in the scientific part. And so what we did is we built the MaMBA laboratory. And we built this in 2019. And as you can see in my background, so I'm sitting inside the MaMBA laboratory right now. And the inner diameter is about 4.40 meters. And some people say, oh, it's more spacious than I anticipated. And some people say it's quite tight in here, quite cramped. But for us, or for me, the question was, if you have a laboratory, I'm physicist engineer. I don't usually work in the laboratory. But if we had scientists that actually normally work in a laboratory, we put them in here, and they're supposed to conduct experiments, can they actually do that? And so yeah, that's what we did. That's what we did exactly. We invited. I have a picture here. We invited a team of scientists, and they prepared their protocols beforehand for experiments like they would be conducted on Mars. And then they were conducting those experiments inside this laboratory over the course of about one week. So they didn't sleep in here, they didn't eat in here. They only conducted their experiments, and then in the end we asked them, is the space, the design of the space, is it something that you can work with? And luckily, their response was yes, the size is okay, and also the design is something where we can work. So we moved into the humans in the loop testing. So after this experiment, and I said these test runs were conducted in 2019, and it was just before Corona. So during Corona, it was a bit difficult to have, a crew, however small, inside a confined space. So that's why we didn't have so many simulations during that time. But now that we are more flexible here, one of the recent simulations that we did is together with the Columbus Control Center, so the control center that normally operates the Columbus Center of the International Space Station. And we did a joint simulation. I will get back to that in a minute. And we are also doing experiments together with the Austrian Space Forum that typically conducts analog missions in remote areas, typically deserts. They've been to Israel, they have been to Oman, and there they typically invite scientists to add their studies to them, either for some hardware tests or for psychological studies. And so that's what we have done in 2020 together with Vera Hagemann had a nice experiment there where we were studying the interaction between different teams. So within the crew, and then the crew interacting with mission control. And also the crew, no, not the crew, those two interacting with the remote, the on-site support. And currently we're preparing for another mission that's not so much for psychology, but it's really for technology testing. And where we're interested in, so I mean, it's all about how to support the crew, from habitat design by itself. But, if we have if we're building a life support system, and we have an artificial intelligence or a network that is giving data to the crew, then over a user interface, then the user interface should be integrated into the habitat in a meaningful way, in an accessible way, or user-friendly way, so that the crew they should not have to look for the necessary information. I mean, the worst case is, there's a problem with the life support system and it's not producing oxygen anymore, and then the crew needs to find out real quick what to do. So this is one of the things. So this would be habitat design, to support the crew through habitat design. But then if we present the data in a way to the crew that they can process it very quickly, that would be support through artificial intelligence or any kind of algorithms. And then there's a third component. There's mission support, because especially the early missions, they will be supported from the ground. And this is where the collaboration with the Columbus Control Center comes into. And in terms of habitat design, we had some nice, fun little projects with some architecture students and some design students who were looking into, how to make the habitat more livable and more flexible. So this ties into how to change the interior of the habitat in a way, that it's not just about changing colors. That's easy. You have some, you have some lights, and you can have green light, you can have red light and blue light, whatever. That's quite easy, and that's quite standard, I would say, in many habitats on, Antarctic bases, for example. But here we were really looking into what more can we do? Can we change the textures and the forms and the shapes inside not obviously inside the laboratory. I'm afraid we're not that flexible there, but for example, for the leisure room or even for the kitchen room. And so here on the bottom left, you can see some design ideas how this could be achieved with some lightweight materials. But getting back to the Columbus Control Center simulation, because I was rushing through that a little bit. So the idea here was, like I said, we had a crew member inside the MaMBA habitat. So basically, almost exactly behind my back, working on a habitat subsystem. So a subsystem of a life support system inside the habitat, and you can see it here, sort of in the middle of the picture. This is a photobioreactor. I will explain a bit what a photobioreactor is in a minute. But for the sake of this experiment, the idea was that this crew member is not normally working with the photobioreactor, but let's say the person normally working with the photobioreactor is not available, but there is some problems with the photobioreactor. Now this crew member has to repair or do some maintenance to get the photobioreactor back up and running so that the crew, has oxygen to breathe. And how to do this is, in space, we always have procedures for everything. So they already know what to do, but then it's much easier and much faster and also much safer if they are guided and helped by the control center on the ground. So this is really the flight controllers and flight directors in the control center. They have more or less the same information as the crew, but they can help the crew and direct them and keep track of timing and give them tips. And also they can do a lot of, monitoring of data that take a lot of load off the crew. That's what they're there for. And so for our simulation, we had someone at the Columbus Control Center helping our participant inside the MaMBA module working with this photobioreactor. And just like in real missions, how it's done on the ISS currently, is that the Columbus Control Center was contacting us, or was in direct communication with us here at the ZARM outside the MaMBA module, whenever there were questions that the flight director was not able to answer, then he would relay between us and the crew. And the fun part here is, the Autonomous Control Center is used to orbital operations where you don't have any time delay. And the question for us and them as well is now, how does this change? How do the operations, the concepts of operations and the procedures, how do they need to be adapted to, accommodate for the time delay? And so that's why we had, different scenarios for our simulations. We had, a no time delay simulation as a reference, comparable to what we have on the ISS, and the Mars time delay. And it was quite fun to see how the communication changed very quickly and very drastically between these two. So this will affect, obviously this will affect procedures and how things are done, but it also will affect how we need to design the habitat because, the crew needs to be much more autonomous than they are currently on the ISS. Okay, I promised to explain what the photobioreactor is there for. And photobioreactor really is for the non-biologist. If you're a biologist, you may want to close your ears. For a non-biologist, it's basically a tank with water, and you have cyanobacteria or algae or any microorganisms inside. And then you shine some light into this tank, and you add some nutrients. You control pH and temperature and all those things. And then ideally, if you did everything right, then these microorganisms inside, they grow and they do photosynthesis. They produce oxygen and they also bind the carbon dioxide that the crew exhales. So that's what a photobioreactor does. And this is what we have been building. Paul, a PhD student, has been building this photobioreactor. And for us, at the moment, the focus is not so much really to create a functioning life support system. There are people who are better qualified to do that. For us, the interesting part is to have a photobioreactor that we can use for exactly this in the humans in the loop testing. Because now we have a real piece of hardware that, where the microorganisms need to be kept happy and alive for the crew to have oxygen. And so we have some components that would be realistic for a life support system, and we can adapt the procedures there and the operations. So that's the side effect. And the reason why we're able to build this photobioreactor, like I said, a physicist and engineer, I'm not a biologist, but we had help from a biologist, the Cyprien Rasseux, who is the head of the Laboratory of Applied Space Microbiology here at the ZARM. And so photobioreactors or life support system components for habitats, is one aspect of our collaboration, but also we had another collaboration that's more his project, but then we were helping in the construction of the hardware, where he's investigating, still cyanobacteria and producing oxygen, but he wants to see, one of the questions he's trying to answer is if cyanobacteria could thrive under conditions in a photobioreactor that are closer to Martian conditions than to terrestrial conditions. And the reason why this is interesting is because maybe you don't want to have the photobioreactor inside your habitat. Could be one option. If it's a direct component of your life support system, it might be good to have it inside the habitat, because then if anything fails, you can access it directly. But especially if you want to produce larger amounts, or if you want to not only produce oxygen, but also other chemicals or biomass or whatever, then it might be better to have this outside. And then, of course, you don't want to have your photobioreactor under 1 bar atmosphere, and also not, atmosphere that is breathable for humans, but maybe an atmosphere that is more suitable for cyanobacteria. And so together we built this photobioreactor that you can see here to answer exactly those kind of questions. Speaking of biology, and this is the last topic that I will be covering in this presentation, but which for Mars is extremely important, and can have, this could be a deal breaker in the worst case. So one thing I mentioned in the beginning that we're working on is the Airlock. And for Mars, we need a new airlock, to put it simply. And why do we need a new airlock? So there is already an airlock on the International Space Station. It's called the Quest module. And the thing is, we cannot use this airlock, not even remotely, for Mars. One thing is, well, it's in orbit, so there's no dust. Dust will be a problem on Mars. Probably the bigger problem is, maybe bigger problem, when the airlock on the ISS is being used, which happens about once a month on average. That's not very often. And when they use this airlock, they evacuate the airlock down to about 1/3 of a bar. They pump that air into the remainder of the ISS, and then this 1/3 of a bar is just vented into space. Now imagine Mars, where we will have EVAs more often than just once a month. So NASA is currently planning with 2 to 3 EVAs per week. And now imagine every time the crew is going outside, you have 1/3 of your airlock that you're venting into us. That's quite a lot of resources that you're losing there, and that you would need to get from somewhere else or bring from Earth, which is quite costly. So that's the second issue. And then the deal breaker issue really is this little guy right here. As I said in the beginning of the presentation, one of the main scientific reasons why we're going to Mars is because we want to find, hopefully, maybe not hopefully, traces of life. And those life forms, they will likely not look like this guy. They will be, it's more likely that if they are actually existing, that they would be microbes. But the thing is, if there really are living Martian microbes, indigenous Martian microbes, then we do not want to bring them to Earth, because we have no idea what would happen to our ecosystems here. And vice versa, if we're sending humans to Mars, we will bring our microbes and we will spread them everywhere, unless we do something to reduce this microbial load on potential Martian ecosystems. And that's the thing. Today on the ISS, we don't have to worry about this microbial contamination. But if you're going to Mars and we do well to do it in a way that we do not destroy any potentially existing ecosystems, we should do it in a way that we are not, contaminating it left and right whenever we leave the habitat. So one solution to this problem of reducing contamination in either direction would be to not use airlocks at all. You could imagine having a suit attached to the outer shell of the habitat. And so instead of using the airlock, from the inside of your module, you climb through the back of the suit into the suit. And so the Russians, they have been doing this for decades with their spacesuits. So their rear entry spacesuits. And this door kind of thing is called a suit port. And if you followed the news on the Artemis missions, then you will see that the suit that NASA and Action Space have presented for the Artemis missions is also a suit that is using a suit port, so a rear entry suit. So, the nice thing is, when you go on EVA, you climb directly through the habitat wall into your suit, and then you detach the suit and you can go about. And when you come back, you just attach it to the wall of the habitat, and the outside of the suit never actually gets into the inside of the habitat. This sounds awesome in theory. We will not bring microbes and dust inside, but there's a catch. And the catch is that this it works. So the system works, but every time you go on EVA, you sweat into the suit. So we will need to clean the suit. Every time you go on EVA, there will be some wear on the suit. The gloves will be worn after a couple of EVAs. The rocks are relatively sharp. The boots will need to be replaced at some time. The kneecaps will need to be replaced. During the Apollo missions, the visors were completely scratched at the end. So those will need to be replaced. And this cannot be done when the suit is attached and pressurized on the habitat wall. So suit ports are awesome, but they are not the solution. They just shift the problem. They reduce the problem. So we still need an airlock. And the idea now with the airlock concept, SafeMars, that we have been developing, So here you can see the Airlock module, and on the side you can see the entry ports for the suits. But every time you need to bring the suits inside, you would actually go through this airlock here. And now the idea is, inside this airlock, there will be some disinfection. And you could use many chemicals for that. You could use hydrogen peroxide, you could use water vapor for disinfection. The chemical that we decided for now is ozone, which has the great advantage that you can produce it on Mars. And also when the disinfection is done, then ozone decays by itself. And this disinfection process can be overlapping with the with the depressurization and repressurization of the module. And so the idea is, this is similar to biosafety laboratories here on Earth, where they work with Ebola and where they don't want the Ebola virus to come outside with the people working there. So it's a very similar concept, not identical, but a similar idea that when you go on EVA, first you enter a pre or an ante room where you change your clothes, you go into a shower, clean yourself, you put on some gloves, and then only then afterwards, once you're clean, you've washed the grime off your hands. That's when you go into the actual suit donning area, and then you put on your suit with the gloves, with the protective gloves, and then once the suit is on, then you can remove the protective layers. There will still be some microbes on your suit, but then the final step, like I said, is going into the actual airlock and disinfecting. And same, then you go on EVA, and then when you come back in, again, you need to disinfect, because that's probably the more critical part, because we don't want to bring the Martian microbes into the interior of the habitat. To summarize this presentation, very briefly, so what we covered, so you can see an overview of the entire MaMBA habitat concept with the 6 modules and the 2 airlocks. 2, because if one fails, the crew should still be able to enter through the back door. And on the right-hand side, you can see a model of one of the modules. And so there are basically 5 aspects to this work that we covered. One, as you know, the MaMBA concept itself, which can serve as a functional extraterrestrial habitat, as a prototype or as a baseline for further studies. And we looked into more detail in the airlock, in the exploration airlock, which, like I said, has to be completely from any existing systems. We don't have any historical airlocks that we could rely upon. And then looking specifically into the laboratory module, so we're looking at components of life support systems and some infrastructure, building our own subsystems, not a full-scale life support system. And we tested with humans in the loop, and we put a lot of emphasis on supporting the crew through habitat design, through the control center, so humans, and through artificial intelligence, algorithms, whatever we can have available for our Mars crew. And we looked into the laboratory design and made sure that this is something that a crew on Mars can actually work with. So with this, I'm at the end of my presentation, just one. And if you have questions, please go ahead.